free body diagram is a backbone or a foundational piece in engineering mechanics. And we're going to go through the steps that we would take to draw a free body diagram. It takes a lot of practice, but the reasons we do draw free body diagrams is to communicate to others what it is we're looking at, to make it clear for ourselves what we are analyzing and designing, and including all these things on there makes it very easy for us to do our calculations we need to find our unknowns and to solve our problems. But ultimately what we're trying to do is analyze and design components of or structures. So the steps we go through to draw a free body diagram is if we decide what it is we are analyzing. So we pick our body, and then we separate that body from the surroundings. So essentially that is free the body, right? We're finding that. Then we're going to indicate on that body all external forces. And we're going to include the weight at the center of gravity and all magnitudes and directions on that body. As much as possible, we're going to draw to scale. We're going to indicate all reactions from supports. We're going to look at magnitudes and directions, and we're going to include all dimensions and angles in our drawing. So like looking at the Eiffel Tower, first thing we have to decide is what it is we're analyzing. What is the body we're going to be looking at? We could look at a single member, a single strut, a single truss member, a single connection. We could look at the top half. We could look at the bottom half. We could look at some intermediate piece. Wherever we cut it and free it from, then we need to apply all the other forces that are acting on it from that point, and so on. We could look at this as the whole body. And we're going to try to draw with a straight edge, and we're going to try to draw things as much as possible to scale. But for right now, let's just draw the entire Eiffel Tower in a two-dimensional shape and a two-dimensional free body diagram, looking at it holistically as the whole shape. So we start by drawing the relative shape of the Eiffel Tower. Now it doesn't look anything right. I have this little trick where I can straighten out my member, but we should be drawing with a straight edge, and we should be just drawing it as much as possible to the actual shape. So anyway, that's the basic shape of it. Then we apply all external forces. So the only thing external that we're looking at at this time is the weight, and we'll put it at the center of gravity. If we have a triangular shaped member, the center of gravity is about a third of the way from the bigger end of the triangle, and that is where we're going to apply our weight. And then we need to show our supports. We can pick a different color here for supports, for support reactions. And in this case, we're showing it in 2 dimensions, but it's really a three-dimensional shape. And so we have 4 legs. That's where the 4 came from. Instead of just 2 legs that I'm showing here. But we would, the reaction here on the left would represent 2 legs, and the reaction here on the right would represent 2 legs. So now we've gotten our reactions on there. We've showed, if we knew the magnitude of them, we would put that on here. We don't know that. But then the last thing that we need is any kind of measurements that we need. And so we don't really know what it is, but we're just going to put it on here and say that this dimension line here, from here to here, that this distance is d. And that's basically a free body diagram of the Eiffel Tower. Very rudimentary, but that's it. That's enough for me to analyze what is the reaction on the ground of the supports of the Eiffel Tower, if that's what I'm looking at. On our other picture here, we can see there's a lot of things going on, and there's a lot of different members and structure happening. And we could look at any piece of that, or any column or beam, or so on. But I like to point out the crane in the background, and unfortunately I can't see the whole thing, but this crane is supported on a single column, and we have a boom, which is the beam that goes across. Essentially this is our boom, and we can draw a free body diagram of that boom. I'd like to point out a couple things in looking at this. So on this end here, you can see the pulley system here, and it was evening, so they weren't working at the time. This isn't a working crane; it will be working the next day. But this is what is used to lift something with the crane. So this side we would have the weight of whatever we're trying to lift, and on this side it's a little hard to see back here. It's hidden by the trees, but what this is ballast. These are actually these giant concrete plates that they put in there to balance off the load. So we're going to draw a free body diagram of this boom. So let's start by drawing our basic shape of our boom and free it from the supports, free it from its surroundings. That didn't work out very well. Let me try that one again. Still. There we go. So I'm giving the boom a little bit of thickness, a little bit of shape. So there's the basic shape of our boom. And then we're going to add, and we freed it from its surroundings, so step one, we've got that. Next we're going to apply any kind of external forces on the body. So with that, we have the weight of the body, so we put that in the center of the body. At its center of gravity. There's the weight. We have the crane that will be pulling down here, whatever that load would be. We can call this the crane. Then we also have the ballast, which is acting back here, pushing down. There's our ballast. We also have these cables that are pulling on our member. Let's pick a different color for those. So here and here, you can see we have cables that will be pulling in tension on the boom. My angle is a little bit steep there. So we try to draw this to scale. There is our the cable. We'll call this one tension 1. A cable is always in tension. It's always a pulling force. It's pulling on the member there. If it was in compression, it would just slack. Okay, and then the other one here goes from this point. We'll call that T2, the tension number 2 there. Okay, so I think that's our external loads that we have from this boom. And then we have our support here, our reaction, which is the column support here. We'll call that one R. And I suppose we could put the top part of this here is probably pushing down here as well. We can call this one, I don't know, it's a compression ARDUC. I can only think of letters that have already been used, so I'm not sure. I hadn't planned to put that there, but I do think that it would be pushing down here. So we will just include this as R2. And we can have this one be R1. They'll be adding together to be the final reaction there. All right, I think I have all the loads now that are included on this boom. And now we need to just add our dimensions and we can put those on here, our dimensions and our angles. A dimension line. I am going to just call the dimensions D1, D2, D3, D4, D5, and D6. There's the free body diagram of the boom. And one other thing we need is the angles here. I don't really know what they are, so we're just going to put them on there as theta and alpha. In reality, we probably would know our dimensions and have some more information here. But this is the free body diagram of the boom. And if I'm trying to see whether or not it would be balanced, if I knew that I needed to pick up a certain amount of load here, then I could analyze this boom to see if it's going to be able to support that or if it's going to tip over. So that's the basics of drawing a free body diagram. Essentially, free that body and add all the external loads and reactions to it, include any dimensions and include any angles, and you can then, using our equation of equilibrium, solve for any unknown forces. Just takes a lot of practice. Good luck to you.